Hi, welcome to Code with Z. In today's video, we gotta find all the unique paths that we can take to go from this position here all the way to this position that we have here. Why? Well, because that's what LeetCode 63 Unique Paths 2 is asking us to do. As you can see, we're given an m by n integer array grid, so basically a grid that we see here, and it says that there's a robot initially located at the top left corner, basically grid at the first row and the first column. Grid at the first row and the first column. So this position that we have here, and we can see our cute robot. And then we're told that the robot tries to move to the bottom right corner. So basically the cell at the last row and the last column, which means this cell that we have here, last row, last column. All right. And then we're told that the robot can only move either down or right, so we can't go left or up, okay? But we're not done yet. Here it says we also have an obstacle, like the one that we see here. As you can see, we have an obstacle, and it says in the grid that's given to us, an obstacle is represented by 1. So if we have 1, that means there's an obstacle. Which grid am I talking about? The grid that was given to us in the beginning, the m by n grid that's given to us. And then at the end it says return the number of possible unique paths that the robot can take to reach the bottom right corner. All right, let's do that. So we got to find the unique paths that we can take to reach this position that we have here. So let's see how we can solve this. Let's see how we can actually find the number of unique paths available to reach this position. There might be only one, or there might be like 20. I don't know. One path could be going here and then this, because we can only go right or down. Or one path could be doing this and then this. One path could be, I don't know, doing this like so and then this. So we need to find how many unique paths we have to reach this position from this starting point. Well, let's start with the basics. How many unique paths do we have to reach our starting point? Well, basically 1, because we just start from this position, right? So just know that we have 1 unique path in this cell that we have here. All right, how many unique paths do we have to reach this position here? Well, I mean, we can't go down and then, I don't know, do this and come back, because we can't do up and left. The only possible way to reach this position is to go right. So there's only 1 unique path. If you think about it, there's only 1 unique path to reach this cell, and that's if we actually go from here to right, like so. So we only have 1 unique path. What about this cell? Well, if we think about it again, there's only 1 unique path to reach this cell as well. We can't do this because going up is not allowed. So the only possible way to reach this cell is to just go right from the starting point. That means there's 1 unique path available to reach this cell, like so. And then if we think about it, same thing for this one, and this one, and this one, and this one. Because, for example, even if we want to reach this cell, we can only go from this position to the right to reach it. Even if we're here, we cannot go up to reach this cell. So there's only 1 unique path, and that's if we only go right from the beginning. Now let's think about how many unique paths we have to reach this position that we have here. Well, we can go from this position to down, and that's gonna be 1 unique path. And let's see if we can do anything else. Well, we can actually do this, but we can't go left or up. So we can't come here and then do up. So there's only 1 path. Again, there's only 1 path. We can only go from this position to this position. So there's gonna be only 1 unique path. What about this one? Well, same thing. We can only go from this cell to this cell and then to this cell. So we have 1 unique path to reach this cell, like so. Now, why did we actually find these unique paths? Well, if you think about it, we're looking for the number of unique paths available to reach this cell. So if we actually calculate the number of unique paths available to reach the cells around it, we can easily find the number of unique paths available to reach the cell itself. And you're gonna see this in a bit. So we've actually calculated the number of unique paths available to reach all of the cells in the first row and the first column. So let's actually take care of the rest that we have here. Well, for starters, this is gonna be an obstacle, so there's no possible way to reach this cell. It's literally an obstacle. So this is gonna be 0 because it's literally an obstacle. Therefore, we can't reach this cell. Well, what about this one? Well, to reach this cell, we can do a right and then a right and then a down. That's gonna be it. Because this is an obstacle, we can't pass through it. There's only 1 unique path. So the number of unique paths available to reach this position is gonna be 1. If this was not an obstacle, we could also do down, right, right. But because this is an obstacle, we can't. So this is also going to be 1. And in a way, we could basically say, if we add these two numbers together, we can calculate the number of unique paths available to reach this cell that we have here. Let's put our rock back because it looks better. So anyways, we want to calculate the number of unique paths available for this cell. Well, if we think about it, we can do right, 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 down, or we could do right, right, down, right. So we have 2 unique paths available. There's no other path. And if we think about it, if we add these two numbers together, that's going to give us the number of unique paths available to reach this cell that we have here. And same thing for this one. If we want to calculate the number of unique paths available to reach this cell, we're going to have 1 plus 2, like so, and that's going to give us 3. Why 3? Well, we can do right, 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 down. That's one path. We can do right, 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 down, right. That's also one path. Or we could do right, right, down, right, right, and that's another path. So that's why we have 3 unique paths available to reach this cell. So you get the idea. Each time we want to calculate the number of unique paths available to reach these cells that we have here, we're going to add the number of the cell above it and the cell left to it. Like so, 1 plus 3, that's going to give us 4. And then 4 plus 1, that's going to give us 5 for this one. And that's why we calculated the first row and the first column in the beginning, because the number of unique paths available to reach the cells in the first row and the first column are always going to be 1 if we don't have obstacles. And then we're going to use these numbers to calculate the rest. As you can see, we added 1 to 4 and that gave us 5. So this one that we have here is necessary. Now let's move on to this one. As you remember, this is a 0, so we're going to say 0 plus 1, that's going to give us 1. The number of unique paths available to reach this cell is going to be 1 because we can only go down, down, right. And then for this one, we're going to say 1 plus 1, that's going to give us 2 because we can do right, right, down, down, or we could do down, down, right, right. And then for this one, we're going to do 2 plus 2, that's going to give us 4. And then 4 plus 3, that's going to give us 7 for this one. Then 7 plus 4, that's going to give us 11 for this one. And then 11 plus 5, that's going to give us 16. And that's going to be our answer. And this is our algorithm. So we're just going to fill the first row and the first column with 1s. And for the rest, we're just going to add the number that we have in the cell above it to the cell left to it. And if we have an obstacle, we're going to make that cell 0. That's going to be it. Let's code this in the simplest way possible. Alrighty, so we were given the obstacle grid, and then we have to define our own grid that we slowly filled with the answers. In the first time, we filled the first row with 1s and then the first column with 1s. So we actually have to define our grid. So first of all, let's get the m and n values. M is representing the number of rows and n is representing the number of columns. So const m is equal to obstacle grid dot length, like so. And then const n is equal to obstacle grid at the index of 0 dot length. So now that we have the number of rows, which is m, and the number of columns, which is n, we can easily make our grid that we saw in the slide. So I'm just going to say const grid being equal to array with the length of m. Now the only difference is that we're going to fill the grid with 0s in the beginning instead of it being like empty. So all you need to know that I'm currently making the grid, and I'll explain what this line does in a bit, just a moment, but it's just making the grid. So array with the length of m, and we want to fill this with 0s as well. So what this line is basically doing is that we're going to make an array with the length of m, and we're going to fill it with 0s, and then we're going to loop through each element inside of that array, and we're going to insert another array there, and we're going to fill it with 0s, and that's going to give us our grid. Now let's fill the first row and the first column with 1s, just like we saw on the slide. So we're going to say for let column being equal to 0, and we want to keep on looping as long as column is smaller than n, and column plus plus on each round. And here we're going to say, first of all, if we actually face an obstacle, we need to put 0, not 1, just like we saw on the slide. So we're going to say if obstacle grid in the first row and basically the column, so we're basically looping through all the cells in the first row, just like we saw on the slides. If this is equal to 1, meaning if we have an obstacle, what we want to do is that we're going to say grid at this position should be actually equal to 0. And we're going to break out of our loop. If that was not the case, meaning if we didn't actually have an obstacle, we're just going to do grid 0, and this is going to be basically equal to 1. So we're going to fill it with ones. So that's going to take care of all of the cells that we have inside of the first row. Now we need to take care of all of the cells that we have inside of the first column. So we're going to say for let row being equal to 0, and we want to keep on looping as long as row is smaller than m, and row plus plus on each round. Here we're going to have something similar. We're going to say if obstacle grid at row and the first column is equal to 1, do the following. We're going to say grid at row and the first column should be equal to 0, and then we're going to break. If that's not the case, we're going to say grid at row and first column should be equal to 1. So these two for loops that we have here, this one and this one, are filling the first row and the first column with ones, and if we have an obstacle, we're going to fill that cell with 0. And then we have to do what we saw in the next stage. We were adding the value in the cell above and the cell to the left to find the value of the current cell. So we would just say for let row being equal to 1, and why 1? Because we've already taken care of the first row and the first column. So we're starting with the index of the second row, and the second row has the index of 1. And then we want to keep on looping as long as row is smaller than m and row plus plus. And then we're going to have a nested loop because we want to loop through each cell, not one column or one row. And then we're going to say for let column being equal to 1 because of the same reason. And we want to keep on looping as long as column is smaller than n. And we want to increment column on each round, like so. Here we're going to say, again, if we have an obstacle, so if obstacle grid at the row and the column that we're currently at is equal to 1, do the following. We're going to say grid at that row and that column should be equal to 0, just like we saw on the slides. This is going to be it. We're not going to use break here, and I'll tell you why in a bit. But if that's not the case, we're just going to say grid at row and column should be equal to, now we're going to add those two numbers. We're going to say grid, the cell in the previous row, same column, plus, let me drag this to the left, grid at the same row, but previous column, like so. So we're basically adding the values that we have in the cell above and the cell to the left. And then at the end, we're just going to return the value that we have inside the last cell in our grid. So m-1 and n-1. So basically the cell at the last row and the last column, that's going to be our last cell. Now, the reason that we don't have break just like we had it here is because if we're actually in the first row and the first column, and if we hit an obstacle, for example, if this obstacle was here, there's no possible way that we can actually reach the cell after it. We said there's only one unique path to reach the cells in the first row and the first column, and if we have an obstacle in the way, that means that one possible unique path is also gone because there's an obstacle and we can't reach it. That's why we have a break here. But if we have an obstacle in the middle, we can go around it and find another way. So that's why we're not gonna break out of our loop. Now, there's also one more thing. If we actually have the obstacle in the first stage, we can't return anything. The number of unique paths available to reach our goal is gonna be 0 because the first position that we have literally has an obstacle, so we can't move anywhere. So we're gonna say if obstacle grid at the first row and first column is equal to 1, just return 0 because there's no possible way. Now, let me zoom out a little bit. This is gonna be all of our code. As you can see, let's run it. I hope I have not made any typos. Let's see, moment of truth, and yep, we got accepted. That's awesome. Let's submit it and see if we're gonna pass all of the test cases. And yep, we got accepted. That's awesome. Thanks for watching. Don't forget to like and subscribe and keep on coding.